Dear students, in the previous class, we have discussed in detail how sample statistics is used to estimate population parameters. For example, we have seen how the sample statistics x bar is used to estimate the population parameter mu. And we defined a x bar as a point estimate. We defined x bar as a point estimate. And a point estimate such as x bar of a population parameter give a single value for the estimator. For example, x bar is say equal to 50 or x bar is equal to 100, etc. It provides only a single value to the population parameter. And a point estimate of a parameter is the value of the statistics used to estimate a population parameter, and it is a single value as we have defined. And we also discussed that a sample statistic or an estimator is a random variable. A sample statistic or an estimator is a random variable with a certain probability distribution. And this probability distribution is defined as the sampling distribution. Every estimator is a random variable with its probability distribution, and the probability distribution is known as the sampling distribution. And as we have seen, a given point estimate will give us only a single estimate of the parameter. Also, the actual value of the parameter may or may not be close to the estimate. The actual value of the parameter mu may or may not be close to the estimate, say 50. Because, as we have discussed earlier, as a sample is used to estimate a population parameter, there is always sampling error. Sampling error, we have defined it as the error resulting from using a sample to estimate a population parameter. So, due to sampling error, we cannot expect that x bar will be close to mu or equal to mu. If you take one sample, you will get one value for x bar. Take another sample, you will get another value for x bar, etc., etc. And we cannot say which x bar will be close to mu due to what is known as sampling error. So, if we provide only a point estimate, and that is if we provide only a single value as the estimate of the population parameter, we are not giving any information about the accuracy of the estimation procedure. if we provide only a point estimate of the parameter, we are not going to give any information about the accuracy of the estimation procedure. So, we should accompany any point estimate of, say, mu, a point estimate x bar of mu with what is known as information that indicates the accuracy of the estimates. Along with a point estimate, we should give some information about the accuracy of the estimate, and this information is known as the confidence interval. The confidence interval of the estimate. The accuracy of information, that is the information associated with a point estimate, which give more information about the accuracy of the estimate, is known as the confidence interval estimate of mu. The confidence interval estimate of mu. And the confidence interval estimate of mu will give information about the accuracy of the estimates. As an example, if you say that sample mean x bar is, say, 550, sample mean x bar is 550, is a point estimate of the unknown parameter mu. But this will not give us how close mu is to the estimate 550. How close the parameter mu is to the estimate x bar is equal to 550. Suppose we say that we are 99% confident that 99% confident that the interval, say for example, say 440 to 560. We are 99% confident that the interval 440 to 560 contain the parameter mu. So if we say that mu will lie between 440 and 560 with 99% confidence, this will give more information about the value of mu. This will give more information about the value of mu. So this is an interval. We suggest an interval in which the parameter will lie. And we say that we are 99% confident that mu will lie in this interval. Now suppose that we consider another interval. We are 90% confident that mu will lie in the interval, say 400 to 600. 90% confident that the interval will contain the parameter mu. And as we are only 90% confident that the parameter will lie in the interval 400 to 600, it will give less information about the possible value of mu because the confidence interval is wider between 400 and 600. So we are 90% confident. It will give less information about the value of mu because the interval is wider, and also the level of confidence is now 90% only, it is lower. And these examples give confidence interval estimates of mu. These examples are examples of confidence interval estimates of mu. So, with a confidence interval estimate of mu, we use the mean of a single sample to construct an interval of numbers and state how confident we are that mu lies in that interval. And we call this interval the confidence interval. So let me give a proper definition of confidence interval. A confidence interval estimate of a parameter consists of an interval of numbers obtained from a point estimate of the parameter and a percentage that specifies how confident we are that the parameter lies in the interval. The confidence percentage is called confidence level or level of confidence. So we define two quantities. Confidence interval. One is the confidence interval, and confidence interval is an interval of numbers. Confidence interval is an interval of numbers obtained from a point estimate of a parameter. Interval of numbers obtained from the point estimate of a parameter. And we will see how this confidence interval is constructed. Second is confidence level. That is the confidence we have that the parameter lies in the confidence interval. The parameter that we have that about the parameter, like in the confidence that we have that the parameter lies in the confidence interval, such as say 95%, 90%, 99%, 90%, etc., etc. Confidence level. As an example of how confidence intervals are constructed, we consider an example. The example is the data published by US Bureau of Census publishes annual figures for new mobile homes. Prices of new mobile homes published by US Bureau of Census. We take a random sample of 36 new mobile homes. 36 new mobile homes. And the prices are given in thousands of dollars. In thousands of dollars. The actual data will be, we will do how to construct confidence intervals using actual data. For the time being, suppose that we have n is equal to 36. The prices of homes are given in thousands of dollars. And using these 36 samples, X bar is calculated as 63.28. That is $63,280 in thousands of dollars. So $63,280. That is the X bar obtained from the sample. And this X bar is a point estimate, as is known to you, because it provides a single value to the parameter mu. And now we will see how this X bar is used to construct a confidence interval, having a certain confidence level. Now, and remember also this, X bar is 63.28 or 63,280. Mu is unknown. You will never know what is the average price of mobile homes in US. Unknown. Because, and X bar need not be equal to mu due to what is known as sampling error. Sampling error, as we have defined error earlier, is the error resulting from using a sample to estimate a population parameter. Sampling error is the error resulting from using a sample to estimate a population parameter. Now, in this example, let us see how we obtain a 95.44% confidence interval for mu. 95.44% confidence interval for mu. For that, we assume that the prices of new mobile phones are normally distributed. That is, the population is the prices of mobile phones is normally distributed with the population standard deviation as $7.2 equal to $7,200. We assume that population is normally distributed. Population standard deviation is known. Population standard deviation is 7.2. Now, N is 36. N is 36. Sigma is 7.2. And the prices are normally distributed. Mu of X bar is equal to mu unknown. We do not know. Then sigma of X bar is sigma by root n is equal to 7.2 by root of 36 is equal to 1.2. And we know that X bar is normally distributed. If X is normally distributed, X bar is normally distributed for any sample size. Even if X is not normally distributed, X bar is normally distributed provided that N is greater than 30. That is the central limit here. Now, the 95.44% of a rule which we have discussed earlier, 68.26, 95.44, 99.74. 95.44% of this rule states that for a normally distributed variable, 95.44% of all the possible observations lie between plus or minus 2 standard deviation of mean X bar. That is 95.44% of all possible observations of X bar lie between plus or minus 2 into standard deviation of X bar. Let me say what it is. Suppose that this is the distribution of X bar and also that this is the mean of X bar. Mean of X bar is unknown to us. Then what we say is, if we take mu plus 2 into sigma by root n, mu minus 2 into sigma by root n. If we take mu plus or minus 2 sigma by root n, 95.44% of x bar lie in this interval. X bar lie in this interval. So, in our example, what is the mean? The mean is, as we have calculated, the mean of the sample is 63.28. Sigma of x bar is 1.2. 1.2. So, 2 into, so mu plus or minus 2 into sigma by root n, 1.2. So, mu plus or minus 2.4. So, 95.44% of x bar lie between what is known as 2.4 here, 2.4 here, 2.4 mu plus or minus 2.4 on either side of the mean. Because x bar is a normally distributed random variable and the area property is applicable to x bar. Plus or minus 1, 68.26, plus or minus 2 sigma, 95.44, plus or minus 3 sigma, 99.74. We can also say that 95.44 of all samples have the property that the interval x bar minus 2.5 to x bar plus 2.4 contain mu. So, 95.44 written in this form is x bar is equal to mu plus or minus 2 into sigma by root n. And in terms of mu, we can write mu is equal to x bar plus or minus 2 into sigma by root n. Again 95.44. So the statement is 95.44% of all samples have the property that the interval from x bar minus 2.4 to x bar plus 2.4 contain mu. Hence, the chances are 95.44% that the samples we obtain have this property. So, we can be 95.44% confident that the sample of 36 new mobile phones whose prices are given has the property that the interval x bar minus 2.4 to x bar plus 2.4, x bar minus 2.4 to x bar plus 2.4 contain mu. And this is written as 63.28 minus 2.4 is equal to 60.88 and 63.28 plus 2.4 is equal to 60. So the 95.44% confidence interval for mu is this, that is 65, 680, 60, 80, 880. This is the 95.44 confidence interval for mu. So what we do in the context of interval estimation is, instead of depending on a single estimate, we construct an interval around the estimated value by using 2 or 3 standard deviations on either side, and we construct an interval and say with some confidence that the parameter will lie in this interval. Now, this interval is a random interval because the interval will vary from one sample to another sample. If you take one sample, this is the interval, take another sample, x bar will be different, so interval will also be different. And what this rule says is that, suppose that this is mu, the position of mu. If you construct confidence intervals in a repeated number of times, say 100 times or 1000 times, this rule says that 95.44% of such intervals will contain mu. So, mu contained in this interval, mu contained in this interval, mu contained in this interval. Only 4.66% the interval will not include mu. It is like this. That is, the mu will not be in this interval, say 5 out of 100 times. Mu will be in this interval 95 out of 100 times. The exact values will be discussed later. So this is the idea behind confidence interval estimation. Instead of depending on a single estimate, we construct an interval around the estimated value and say with some confidence that the interval will include the true but unknown parameter. This is the idea behind interval estimation. And in the next section, we will consider how confidence intervals are constructed for population mean when sigma is known. Sigma, population standard deviation, is known.